You are certain, right now, that you are sitting perfectly still. The floor is steady, the room is quiet, nothing about you is moving. It is the most obvious fact of the moment, and it is completely false. The ground beneath you is spinning eastward faster than the speed of sound, around 1,000 miles an hour. The planet under that is racing around the sun at 67,000 miles an hour. The sun is hauling you around the galaxy at 500,000 miles an hour, and the whole galaxy is falling through the universe at more than 600 kilometers every second. You are moving in 4 directions at once, at speeds you cannot picture, and you feel absolutely none of it. The stillness you trust so completely is the most convincing illusion your body has ever sold you, because you have not been truly still for 1 instant since before you were born. So the real question is not how fast you are moving, it is whether stillness is something the universe will allow at all. Get comfortable, hit subscribe if you're new here, because by the end of this, the feeling of sitting still will never mean the same thing again. Now, let's slowly ease into this. Part 1. The stillness you think you have. Right now, as you settle in to listen, you feel completely still. The surface beneath you holds steady. The walls around you stay exactly where they are. Your hands rest where you left them, and nothing about this moment suggests that you are moving at all. If someone asked you, in this quiet, whether you were in motion or at rest, you would not even have to think about it. You are at rest. You are sitting or lying down, perfectly still, and that stillness feels like the most ordinary and obvious fact in the world. It is the calm background against which everything else happens. Things move. You do not. That, you would say, is simply what stillness is. I want to take that certainty apart tonight, slowly and gently, 1 layer at a time, because it is not true. Not slightly untrue, not untrue in some narrow technical way that only a physicist would ever care about. It is untrue all the way down, at every level reality has. The stillness you are feeling at this very moment is the single most convincing illusion your body has ever sold you, and by the time we reach the end of this, you will understand that you have not been truly still for a single instant since before you were born. You never have been. Nothing in the universe ever has. There is a quiet question hiding underneath all of this, and I want to put it into words before we go any further, because the whole night turns on it. What is wrong with stillness? It sounds almost too simple to ask. Stillness seems like the easiest thing in the world, the thing that happens when you stop doing anything at all. Sit down, hold your breath, let your muscles go quiet, and surely you arrive at it. Surely rest is the natural state. The thing the universe falls back into the moment, nothing disturbs it. And motion is the exception, the thing that has to be caused. That picture feels so obvious that almost no one ever questions it. And almost no one realizes that physics, every branch of it, quietly disagrees. Consider how completely you trust this feeling. You build your entire sense of the world on it. When you set a cup of coffee on a table, you call it still, and you are confident the coffee will be exactly where you left it when you come back. When you lie in bed at night, you feel the bed as a fixed, motionless island holding you steady while sleep comes. The ground under a house, the floor of a room, the chair in the corner. These are the things you reach for when you want to describe what it means for something to not be moving. They are the very definition of rest. And every one of them, without exception, is racing through space right now at a speed that would be difficult for you to even imagine. You cannot feel it, and that is the first and gentlest part of the trick. Your body has no way of sensing steady motion. It can feel a sudden change, the lurch when a car brakes hard, the drop in an elevator, the push back into your seat when a plane accelerates down a runway. But smooth, constant motion produces no sensation at all. If the motion never speeds up, or slows down, or turns, your body simply has nothing to report. So you can be carried along at 1,000 miles an hour in perfect smoothness and feel exactly as you would feel if you were nailed to the spot. The absence of a feeling is not the absence of motion. It only feels that way, and your whole life you have mistaken one for the other. You know this already from smaller examples, even if you have never thought of them in quite this way. When you fly in an airplane at its cruising speed, perhaps 900 kilometers an hour, you can stand up and walk to the back of the cabin, pour a drink, and watch it sit perfectly level in the cup, as calm as if the plane were parked at the gate. The motion is there, enormous and relentless, carrying you faster than any animal has ever run, and yet inside the cabin everything behaves exactly as it would if nothing were moving at all, because everything in the cabin is moving together. Only when the plane hits a patch of rough air and suddenly changes its motion do you feel anything, and what you feel is the change, never the speed. The steady rush of the journey is completely invisible from your seat. Now take that same blindness and scale it up from a plane to a planet, from a planet to a galaxy, and you begin to see how a body moving in a dozen directions at tremendous speed can feel for all the world like it is resting quietly in a still room. Think about what that means for a moment. Every sensation of rest you have ever had, every peaceful, settled, grounded feeling of being still, was your nervous system reporting that nothing was changing. It was never reporting that nothing was moving because your nervous system cannot tell the difference. It was built to warn you about the lurch and the fall, the sudden start and the sudden stop, because those are the things that, long ago, meant danger. Steady motion was never worth feeling, because steady motion never hurt anyone. So, evolution simply left it out. You were given a body that is blind, from the inside to the most relentless fact about your existence. You move, always, in every direction, and you have never once felt it. Tonight we are going to peel that blindness away, layer by layer, and look directly at the motion underneath. We will start close to home, with the spinning and circling of the ground beneath you, the motion that is easiest to measure and easiest to accept. Then we will go further out, following the planet around its star and the star around the galaxy, and the galaxy through a current of other galaxies, until the speeds become almost meaningless, and the idea of a single fixed place to stand simply dissolves. And then, when you are ready, we will turn inward instead of outward, down into the atoms of your own body and the empty space between them, and we will find that the motion does not stop there either. It never stops. It cannot stop. That is the thing I most want you to understand by the end, because the real surprise of this story is not that we are moving fast. Fast is easy to picture. The real surprise is what happens every time someone has tried, in theory or in a laboratory, to find or to make a single thing that is genuinely, perfectly still. Every time, at every scale, they have failed. And they have failed for a different reason each time, as if the universe had set up several independent locks on the same door, just to be sure. There is a law that forbids stillness out among the galaxies. A completely separate law forbids it down among the atoms. Third law forbids it in the cold, and a fourth forbids it even in a box with absolutely nothing inside. We will meet all of them. So let yourself stay exactly where you are, comfortable and apparently motionless, and hold on to that feeling of rest for just a little longer, because it is about to become the most interesting thing about you. The stillness you are so sure of is the doorway into everything strange about the universe. We only have to ask one honest question and follow it without flinching. You feel perfectly still. So tell me, as we begin, how fast are you actually moving right now? The answer starts with the ground itself, which has been quietly carrying you eastward this entire time, faster than the speed of sound. Part 2. The motion you cannot feel. The ground you are resting on is turning, and it is turning quickly. The earth spins once on its axis every day, and that is the gentle, familiar motion that gives us sunrise and sunset, the slow wheel of the sky. But a planet is a large thing, and to carry its whole surface around in a single day, the surface has to move fast. If you are near the equator, the ground beneath you is sweeping toward the east at around 1,670 kilometers an hour, which is a little over 1,000 miles an hour. That is faster than the speed of sound. You are sitting still, by your own reckoning, on a floor that is breaking the sound barrier. Let that picture settle for a moment, because it is a good first taste of how strange this is going to get. A rifle bullet leaves its barrel at something close to that speed. If you live closer to the poles, the ground carries you a little slower, because the circle it traces each day is smaller, and at the exact poles you would only turn slowly in place. But for most of the people listening to this, the surface of the planet is hauling you eastward at roughly the speed of a bullet, smoothly and silently, and you feel none of it. The coffee does not slosh. The lamp does not sway. Everything in the room is moving together at the same speed, in the same direction, and so within the room, nothing seems to move at all. That last point is the whole secret of why you cannot feel it, and it is worth understanding properly, because it is the same secret that will hide much larger motions from you later. When everything around you moves together, in the same direction at the same steady speed, there is no internal sign of the motion. Every object keeps the same position relative to every other object. The cup stays on the table. A dropped key falls straight to the floor at your feet, not slanting off to the west, because the key was already moving east at 1,000 miles an hour along with you and the floor and the air, and it keeps that eastward motion the whole way down. Inside the moving system, everything behaves exactly as it would if the whole system were standing still. A scientist named Galileo understood this more than 400 years ago, long before anyone could measure the speed of the spinning earth, and he explained it with an example that has never been improved upon. Imagine you are below the deck of a large ship, in a windowless cabin, while the ship sails smoothly across a calm sea at a constant speed. Galileo asks you to perform some experiments. Watch fish swimming in a bowl. Watch drops fall from a bottle into a container below. Jump across the cabin and notice how far you travel. His claim, which is exactly correct, is that nothing you observe inside that cabin will tell you whether the ship is moving or tied to the dock. The fish swim the same. The drops fall straight. You jump the same distance toward the front of the ship as toward the back. The reason is that you and the fish and the falling drops and the air in the cabin are all already moving along with the ship. The ship's motion is shared by everything inside it, and so it cancels out of every experiment you could do. Only if the ship were to suddenly speed up, or slow down, or turn, would you feel anything, because then the ship would be changing its motion while your body, for an instant, tried to keep the old one. That sudden change is what your body can feel. The steady part, the constant gliding forward, is completely invisible from the inside. Galileo had put his finger on something that runs to the bottom of physics. Steady motion and perfect rest are, from the inside, exactly the same thing. There is no experiment that can tell them apart. This single insight is the first crack in your certainty, and I want you to feel how far the crack goes. You believe you are at rest. But Galileo has just shown that being carried along at a constant speed would feel precisely identical. So your feeling of rest is not actually evidence that you are at rest. It is only evidence that nothing around you is changing its motion. You could be standing still, or you could be flying along at 1,000 miles an hour, or 10,000, or 100,000. And as long as the motion was smooth and shared, the feeling in your body would be exactly the same calm stillness you have right now. Your sense of rest cannot distinguish between these cases. It never could, so we cannot trust the feeling, and we have to turn instead to measurement, to careful observation of the sky, and the sky tells a clear and astonishing story. The spinning of the ground at 1,000 miles an hour is only the smallest of the motions you are caught up in. While the Earth turns on its axis once a day, it is also racing around the Sun once a year, and to complete that enormous loop in only a year, it has to travel far faster than it spins. The Earth moves along its orbit at about 30 kilometers every second, not every hour, every second. That works out to something like 107,000 kilometers an hour, or 67,000 miles an hour, as you sit there feeling perfectly still. Try to hold that number in a human frame, because a number like that means nothing until you do. At 30 kilometers every second, you cross a distance equal to the full width of the planet you live on in about 7 minutes. In the time it takes to listen to one song, you and the Earth together have traveled something like 5,000 or 6,000 kilometers along the great curve of the orbit. Since this sentence began, you have moved a few hundred kilometers around the Sun. You did not feel a thing, because you and the Earth and the Moon and the air and everything else are all sweeping along that curve together, exactly as Galileo's ship sails on, and the shared motion hides itself perfectly, just as he said it would. And here is the question that should be forming in your mind, the question that pulls us onward and outward into the night. If the spinning ground and the circling planet are both invisible to you, both hidden by the simple fact that everything moves together, then how many more motions might be stacked on top of these, equally silent, equally unfelt? You have already lost the 1,000 miles an hour of the spin and the 67,000 of the orbit, and you never noticed either. What else are you doing right now that you cannot feel? The honest answer is that the orbit around the Sun is not even close to the fastest thing you are doing tonight. The Sun itself is falling, carrying you with it around something far larger. Part 3. The long fall through the galaxy. The Sun is not a fixed point that the Earth circles in some quiet, unchanging corner of space. The Sun is one star among a few 100 billion, all of them bound together in the slow, turning wheel of the Milky Way, and like all the others, the Sun is in orbit around the center of that wheel. To make its way around such an enormous loop, the Sun moves at a speed that dwarfs everything we have talked about so far. It carries the entire solar system, the Earth included, around the galactic center at roughly 230 kilometers every second. That is around 828,000 kilometers an hour, or about 500,000 miles an hour, and you are riding on it right now without the faintest sensation of speed. 230 kilometers every second is so far beyond ordinary experience that the number almost stops meaning anything. So let me try to anchor it. In a single second, while you take one breath, the Sun and everything orbiting it move a distance roughly equal to the span of a small country. And yet the galaxy is so unimaginably large that even at this speed, a single trip around it takes somewhere between 225 and 250 million years. That span is sometimes called a galactic year. The last time the Sun was in the position it occupies tonight, the earliest dinosaurs were just appearing on Earth. In its entire life, more than 4.5 billion years, the Sun has completed only about 20 of these laps. You are partway through the 21st, moving at 500,000 miles an hour, sitting perfectly still. And even the galaxy is not the end of it. The Milky Way itself is not anchored to anything. It is one member of a small cluster of galaxies, held together by gravity, and that whole group is drifting and falling through a current of motion that runs through the larger universe. When astronomers measure our motion against the most distant reference they have, the faint background glow of heat left over from the birth of the universe itself, they find that our local family of galaxies is sweeping through space at something over 600 kilometers every second, pulled toward a particular region of the sky. We are not floating quietly in the cosmos. We are falling, fast, in a definite direction, dragged along by the gravity of structures so large they are difficult to even name. You might wonder how anyone could possibly measure such a thing, the motion of our entire galaxy through the universe, when there is no signpost out there to clock ourselves against. The answer is one of the most elegant measurements in all of science, and it uses that faint leftover glow from the birth of the universe, the background of microwave heat that fills the sky in every direction. If we were truly sitting still within that glow, it would look exactly the same all around us, the same gentle temperature on every side, but it does not. The glow is very slightly warmer in one particular direction, and very slightly cooler in the direction directly opposite, by just a tiny fraction of a degree. That lopsidedness is the fingerprint of our motion. We are moving toward the warm side, and the light reaching us from ahead is crowded and shifted to a slightly higher temperature, while the light from behind is stretched and cooled in just the way the pitch of a siren rises as it races toward you and drops as it speeds away. From the size of that warm and cool imbalance, astronomers read off our speed, and it comes out to more than 600 kilometers every second. What is pulling us along is harder to name because it is so large. Our galaxy and its near neighbors belong to a single enormous gathering of galaxies that astronomers have mapped and named, a structure holding something like 100,000 galaxies, all of them slowly streaming along shared currents like leaves carried on one great river. Part of what draws us is an immense concentration of matter off in one region of the sky, a gravitational pull so strong it has been tugging on our whole neighborhood for billions of years. And part of it, strangely, is a push, a region behind us that is emptier than average, and emptiness in a universe full of gravity behaves almost like the top of a hill we are rolling away from. So, we are pulled from ahead and pushed from behind at the same time, sliding across a structure 100,000 galaxies wide, and we feel not the faintest hint of any of it. Let me slow down here and simply let you feel the stack of it, because this is the moment where the word still finally comes apart in your hands. Picture yourself exactly where you are. You feel motionless. Now, feel the ground beneath you, sweeping eastward at 1,000 miles an hour, carrying the room and the building and the city with it. Feel that spinning planet arcing around the sun at 67,000 miles an hour. The whole Earth leaning into a curve so wide you could never see its bend. Feel the sun, and you with it, streaming around the galaxy at 500,000 miles an hour. A slow, majestic fall that will take 250 million years to come full circle. And feel that entire galaxy, every star in it, carried through the larger dark at more than 600 kilometers a second, towards something enormous and unseen. All of these at once. All of them right now. You, sitting still. You are not moving in one direction. You are moving in all of them at the same time, spun and curved and swept and pulled along 4 different motions, layered one on top of another, each one faster than the last, each one perfectly hidden from you by the simple grace of being shared. In the few minutes since you began listening tonight, you have traveled tens of thousands of kilometers through the universe, by every honest measure there is, and the cushion beneath you has never once felt anything but still. The stillness was never a fact about the world. It was only ever a fact about your senses, which were built to ignore exactly this. There is a calmer way to hold all of this, and I want to offer it to you before we go on, because the point is not to feel dizzy or small. Imagine you could rise gently up and away from your own body, up past the room, past the clouds, until the curve of the earth comes into view, turning slowly in the sunlight. Keep drifting and watch the whole planet swing in its wide arc around the sun, a bright ball following an invisible track laid down by gravity. Drift further still, until the sun is just one point of light among a great spiral of them, all of them wheeling together with a patience that spans hundreds of millions of years. And further again, until the entire spiral is a single glowing island among others, all of them sliding together through the dark toward a far horizon. From up here, there is no violence in any of it. There is only an enormous, layered, turning calm, a universe in which everything drifts and nothing holds still, and somewhere down inside it, a single quiet point that is you. Now bring yourself gently back down into the room, and notice that nothing about it has changed except your understanding. The floor is still there. The stillness you feel is still exactly as convincing as it was a moment ago. But you know something now that you did not fully know before. The stillness is local. It is a small agreement among you and the objects right around you, all of you moving together so smoothly that, among yourselves, you seem to be at rest. It says nothing whatsoever about whether you are moving through the universe at large. And by every measure we can make against the larger universe, you are moving through it at a furious, layered, ceaseless pace. This raises a question that is going to occupy us for the next part of the night, and it is sharper than it first appears. When I tell you that our galaxy is moving at 600 kilometers a second, you might reasonably ask, moving relative to what? Speed is always measured against something. The ground moves relative to the Earth's center. The Earth moves relative to the Sun. The Sun moves relative to the galaxy. Each of these motions is measured against a larger backdrop. So when we reach the very largest scale, the whole universe, the natural next question is whether there is some final, fixed backdrop, some ultimate stage that simply sits still, against which all real motion could be measured once and for all. A true and absolute place of rest. For a long time, scientists were certain such a thing had to exist. They had a name for it, and a beautiful idea behind it, and they built one of the most careful experiments of the 19th century, specifically to find it. They were looking for the one motionless thing in all of creation, the fixed floor of the universe, the place where you could finally plant your feet and say, here, at last, is something that does not move. They were looking for somewhere to stand still. What they discovered instead would erase the very idea of a fixed floor from physics forever, and it began the long unraveling of the notion that rest means anything at all. To understand how that happened, we have to go back to a quiet laboratory in 1887 and a search for something that turned out not to be there. Part 4. The search for a place to stand still. For most of the 19th century, physicists were convinced that space was filled with an invisible substance, and they called it the luminiferous ether. The reasoning behind it felt airtight at the time. Light had been shown to be a wave, and every other wave anyone had ever studied was a wave in something. Sound is a wave in air. Ripples are waves in water. A wave, by its nature, seemed to be a disturbance travelling through a medium, and so light, being a wave, surely needed a medium of its own to travel through. That medium was the ether. It had to fill all of space, since light crosses the emptiness between the stars. It had to be thin enough that planets could move through it without slowing down, and it was assumed to be perfectly, absolutely still. That last assumption is the one that matters for us tonight, because it offered something physics had never quite had before. The ether would be the fixed background of the universe, the one thing that truly did not move, the motionless stage on which all the moving actors played their parts. If the ether was at rest, and everything else drifted through it, then at last there would be a real, physical meaning to the words absolute rest. To be at rest would mean to be sitting still relative to the ether. To move would mean to move through it. Here, finally, was somewhere to stand still, a place to put your feet down in a universe that otherwise offered no fixed ground anywhere. All you had to do was find it, and there seemed to be an obvious way to find it. The Earth, as we have seen, is in furious motion, racing around the sun at 30 kilometers every second. If space is filled with a still ether, then the Earth must be flying through that ether, and from the planet's point of view, there should be a kind of ether wind blowing past, the way you feel a wind on your face when you stick your hand out of a moving car, even on a calm day. The ether itself would not move, but our rushing through it should produce the same effect as a breeze. And crucially, light travelling along the direction of that wind should move at a slightly different speed than light travelling across it, just as a swimmer crossing a river and back is delayed differently than one swimming upstream and down. It helps to make that swimmer comparison concrete, because it is exactly the logic the experiment was built on. Imagine two equally strong swimmers in a flowing river. One swims straight across to the far bank and straight back. The other swims the same total distance, but upstream against the current and then back down with it. Even though both swim at the same speed through the water, and both cover the same distance, they do not return at the same moment. The one fighting upstream is slowed badly on the way out, and only partly helped on the way back, and loses more time overall than the one crossing the current sideways. If you race them, the difference in their arrival times would tell you how fast the river was flowing, even if you could not see the current at all. Michelson and Morley were running exactly this race, but with light instead of swimmers and the supposed ether wind instead of the river. One beam of light was sent out and back along the direction the Earth moves, fighting upstream and riding downstream through the ether. The other was sent crossways. If the ether wind was real, the two beams should return slightly out of step, and from how far out of step they were, the two men could read the speed of the Earth through the ether, the very thing no one had ever managed to pin down. The expected difference was fantastically small, a tiny fraction of a single wavelength of light, but their instrument was delicate enough to catch even that. They had built a machine that could time the race between two beams of light to a precision finer than anyone had ever achieved. Everything was ready. All that remained was to run the race and read the result. Two scientists, Albert Michelson and Edward Morley, set out to measure exactly this, and in 1887 they built an instrument of astonishing delicacy to do it. They split a single beam of light into two, sent the two halves on journeys at right angles to each other, one along the supposed ether wind and one across it, and then brought them back together. If the two beams had taken even slightly different times for their trips, the light waves would fall very slightly out of step when reunited, and that mismatch would show up as a distinctive pattern of light and dark bands. The apparatus was sensitive enough to detect the tiny delay the ether wind should produce. They floated it on a pool of liquid mercury so they could slowly rotate the whole thing and catch the wind from every angle. Then they looked. They found nothing, no difference, no delay. No matter which way they turned the instrument, no matter what time of day or what season of the year, the two beams of light always returned in perfect step, as though there were no ether wind at all, as though the Earth were not moving through any medium whatsoever. They repeated the measurement, refined it, ruled out every error they could think of. The result would not budge. The speed of light was simply the same in every direction, regardless of how the Earth was moving. It is often called the most famous failed experiment in the history of science, and the failure was total. The ether wind that had to be there, according to all the reasoning of the age, was not there. This was not a small disappointment. It was a genuine crisis, because the logic that demanded an ether had seemed so solid. For nearly 20 years the results sat in the middle of physics, like a stone no one could lift, prompting increasingly desperate attempts to explain it away, while keeping the ether alive. Perhaps the Earth dragged a layer of ether along with it. Perhaps moving objects physically shrank in the direction of their motion by exactly the amount needed to hide the wind. Clever people proposed clever fixes, each one stranger than the last, all of them trying to save the one thing everyone was sure had to be true. There must be a fixed, motionless background to the universe. There must be somewhere to stand still. The experiment kept saying, quietly and immovably, no. The trouble was that admitting the ether did not exist meant admitting something far more disturbing than a missing substance. It meant there was no fixed background at all. It meant that when you asked, moving relative to what, at the very largest scale, the universe simply had no answer to give. There was no motionless stage. There was no master reference against which all real motion could finally be measured. The flaw of the universe, the thing everyone had been so sure was down there somewhere, turned out to be missing, and beneath it was not a lower flaw, but nothing, no privileged place of rest anywhere in existence. Most physicists could not bring themselves to accept what that meant, because it seemed to pull the ground out from under the very idea of motion. It took someone willing to stop trying to save the old picture and instead ask what the universe would have to be like for the experiment to come out exactly as it did. It took someone willing to give up the comforting idea of absolute rest entirely and to follow the loss of it all the way to its conclusion, however strange that conclusion turned out to be. That person was a young patent clerk who, in 1905, would take the failure of the ether not as a problem to be patched, but as a clue to be trusted. He would assume the speed of light really is the same for everyone, except that there really is no ether and no fixed stage, and rebuild the meaning of space, time, and motion around that single, hard fact. And what he found was that the universe is far stranger than a missing ether. He found that rest itself, absolute rest, is not a real thing that we simply failed to locate. It is a thing that cannot exist. Part 5. There is no rest. The young patent clerk was Albert Einstein, and the theory he published in 1905, which we now call special relativity, begins from a refusal to panic about the missing ether. Instead of asking how to hide the Earth's motion through the ether, Einstein simply took the experiment at its word. The speed of light is the same for every observer, no matter how that observer is moving. He treated this not as a paradox to be resolved, but as a law of nature to be accepted, and then he asked, with relentless honesty, what the world must be like if it is true. The answers reshaped everything, but for tonight, one consequence matters above all the others. If there is no ether, there is no absolute rest. To see why, think again about Galileo's ship, but now take it as seriously as Einstein did. A person sealed in the cabin of a smoothly sailing ship cannot tell, by any experiment, whether the ship is moving or docked. Einstein's insight was that this is not a limitation of our instruments, something we might overcome with a cleverer device. It is a statement about reality itself. If no experiment whatsoever can distinguish steady motion from rest, then there is no real physical difference between them. The question is, there a difference between this ship gliding at constant speed and this ship sitting at the dock has no answer, not because we are too ignorant to find it, but because the universe does not contain the information. Both descriptions are equally true. The ship is moving from the dock's point of view. The ship is at rest from its own. Neither view is the correct one. There is no correct one. Now widen that from a ship to everything. Every object in the universe is like that ship. Each one can rightly consider itself at rest and describe everything else as moving relative to it, and no experiment anywhere can prove it wrong. The astronaut drifting in space says she is still, and the station is moving toward her. The station says it is still, and the astronaut is drifting. Both are completely correct, because there is no third, privileged point of view, no ether, no fixed stage, that could settle the argument by declaring who is really moving. Motion, at its most fundamental level, is not a thing an object possesses by itself. It is only ever a relationship between two things. To ask how fast an object is really moving, with no reference specified, is to ask a question that sounds perfectly sensible and turns out to mean nothing at all. This is the moment to say the thing plainly, because it is the quiet center of the entire night. There is no such place as absolute rest, not somewhere far away that we have failed to reach, not somewhere we might find with a better telescope, nowhere. The stillness you have been longing for, the true and final rest where you are not moving relative to anything at all, is not a distant destination. It is not even a place. It is a phrase that, when you examine it closely under the laws of physics, points to nothing whatsoever. You cannot be still relative to the universe, because the universe is not a thing you can be still relative to. There is no master frame holding the answer. When you finally go looking for the fixed ground beneath all the motion, the place to put your feet down at last, you find that there was never any floor there to find. The search for somewhere to stand still ends not with a discovery, but with the slow realization that the question was empty from the beginning. Sit with that for a moment, because it lands differently than the speeds did. The galaxy moving at 600 kilometers a second was startling, but it left your intuition intact. You could still imagine, somewhere out there, a fixed point, and picture all the rushing motion measured against it. What relativity takes away is that fixed point itself. It tells you the stillness you crave is not hard to reach. It tells you the stillness you crave does not exist and never could, that you have spent your life longing for a state of being that the universe has no room for. You are not failing to be still. You are asking to occupy a condition that is not a condition, like asking to travel north from the North Pole. There is simply no such direction. Stay with how strange that is, because it is stranger than simply being told you cannot have something. You have spent your whole life treating rest as the solid, simple thing, and motion as the state that needed explaining. Rest was home, the place everything returned to, the floor beneath all the activity of the world. And what relativity is telling you is that this floor was never there, that the word rest, when you mean it absolutely, when you mean truly not moving with respect to anything at all, does not point to a real condition that exists somewhere out in the universe waiting to be reached. It points to nothing. It is not that the universe is cruelly holding stillness just out of your grasp. It is that stillness, in the only sense you really meant it, was never one of the things the universe was built to contain. You have been homesick your whole life for a place that was never there. I should be careful and honest here, because there is one thing that sometimes gets mistaken for the old ether, and I do not want to leave it as a loose thread. When we measure our galaxy's motion at 600 kilometers a second, we measure it against that faint leftover glow from the early universe, the cosmic background of heat that fills all of space. And it is true that there is one particular state of motion in which that glow looks the same in every direction, equally warm on every side, with no hot direction ahead and no cool direction behind. You could call that the rest frame of the universe, and in a loose, practical sense, it is the closest thing we have to being still with respect to the cosmos as a whole. But it is not the ether reborn. It is not absolute rest. It is just the average motion of all the matter in the universe, a convenient bookkeeper's frame, and the laws of physics still grant it no special authority. An observer flying through it at half the speed of light is every bit as valid, every bit as entitled to call herself at rest as one who floats within it. The glow gives us a useful average to measure against. It does not give us back the fixed floor that Einstein took away. So the universe offers you no place of rest, not because it is hiding one, but because rest, in the absolute sense, is not among the things the universe contains. And yet, strange as that already is, it is not even the strangest part of what relativity has to say about motion. Because once Einstein had woven space and time together into a single fabric, a four-dimensional thing he called space-time, a new and almost unbelievable picture of motion emerged from the mathematics. It turned out that you are not only moving through space in all those layered ways we have already counted, you are also moving through time, and the two kinds of motion are secretly the same kind, traded back and forth against each other. And when you add up the total, when you measure how fast you are moving through space-time as a whole, every object in the universe turns out to be moving at exactly one speed, the same speed always, the speed of light. Even you, sitting there, feeling perfectly still. Part 6. Moving through time at the speed of light. To understand this, you have to let go of the habit of thinking about space and time as separate things, and instead picture them woven together. In Einstein's universe, an event is not just a place, it is a place at a time, a point in a four-dimensional fabric where the three directions of space are joined by a fourth direction, time. And just as you can move through the directions of space, you are always, unavoidably, moving through the direction of time. The future is, in a real sense, a direction you are traveling as surely as east or up. You do not have the option of stopping. Even lying perfectly still, you are advancing into tomorrow at a steady, relentless pace, carried forward through the time direction, whether you will it or not. Here is the idea that physicists find so beautiful, and that I think is one of the loveliest in all of science. The total speed of any object through space-time, combining its motion through space and its motion through time, is always exactly the same. It is always the speed of light. Nothing can go faster, and nothing can go slower. Everything moves through the four-dimensional fabric at this one fixed rate. What changes is only how that fixed total is divided up between the space part and the time part. An object that is not moving through space at all is devoting its entire share to moving through time. It is racing into the future at the full speed of light, pouring all of its motion into the time direction and none into space. That, and not true stillness, is what it means to be at rest. To sit still in space is to move through time as fast as anything possibly can. And when you do begin to move through space, you do not add to your total speed through space-time, because that total is fixed. Instead, you borrow. Every bit of motion you put into travelling through space has to be taken away from your motion through time. You divert some of your fixed allowance sideways into the space directions, and your progress through time slows down by exactly that much to keep the total constant. This is not a metaphor. It is the literal origin of one of the most tested facts in physics, the slowing of time for things that move. A clock that races through space really does tick more slowly than one that sits still, because it has spent some of its space-time speed on the journey through space and has less left over for the journey through time. Move fast enough through space, and your passage through time crawls. The two are a single budget, traded against each other, always summing to the speed of light. If this sounds like a fantasy that is true only on paper, it is worth knowing that we measure it constantly, in the most ordinary ways. High above your head, when particles from space crash into the upper air, they create tiny, short-lived particles called muons, which fall apart so quickly that even racing at nearly the speed of light, they ought to decay long before they reach the ground. And yet they reach the ground in great numbers every second, all over the earth. The reason is precisely the trade we have been describing. The muons are moving through space so fast that their passage through time is slowed dramatically, their internal clocks ticking far more slowly than ours, and so the brief sliver of life they are allotted stretches just long enough, from our point of view, for them to finish the trip. They are a rain of tiny clocks falling out of the sky, every one of them running slow because it moves so fast, and surviving only because of it. The same effect quietly runs the navigation in your phone. The satellites that tell you where you are carry exquisitely precise clocks, And because those satellites race around the Earth at thousands of kilometers an hour, their clocks tick slightly slower than the clocks on the ground, by an amount the engineers must correct for every single day. If they ignored the trade between motion through space and motion through time, the position the system reported would drift off by kilometers within hours, and the whole thing would become useless. Every time you follow a map on a screen, you are leaning on the fact that moving clocks really do run slow, that motion through space really is borrowed from motion through time. It is not a curiosity tucked away in a textbook. It is built into the machinery of an ordinary day. Let yourself stand inside this for a moment, because it changes what you are. Right now, you feel still, which means, in the language of space-time, that you have poured almost the whole of your motion into time. You are hurtling into the future at very nearly the full speed of light, every second carrying you forward through the time direction at the maximum rate the universe allows. Imagine you could feel that. Imagine the future not as something that arrives, but as something you are rushing toward at the greatest speed there is, your whole being streaming forward through time, because you are holding so still in space. Now imagine standing up and beginning to run, and watching your own progress through time ease back, just slightly, as a sliver of that motion is borrowed away into the space beneath your feet. You will never notice it at human speeds. The trade is far too small to feel. But it is real, and it is happening, and it means that the stiller you hold yourself in space, the faster you fly through time. There is one kind of traveller that takes this trade to its limit, and it shows you the far edge of the idea. A particle of light, a photon, moves through space at the full speed of light, holding nothing back. It puts every last bit of its space-time motion into the journey through space, which means it has nothing left over for the journey through time. And so, for a photon, time does not pass at all. From the point of view of the light itself, the instant it is born at a distant star and the instant it strikes your eye, after a journey of thousands or millions of years across the universe, are the very same instant. It is emitted and absorbed in a single, timeless moment. The light that left a star 1,000,000 years ago has, by its own reckoning, aged not at all. It has traded away the whole of time for the whole of space. You and the photon sit at the two ends of the same law. You give everything to time and nothing to space, and feel perfectly still. It gives everything to space and nothing to time, and never ages a moment. Between you lies every other possible motion in the universe. So here is what relativity has done to the idea of stillness, and it is worth saying without flinching. You cannot be still, in the fullest sense, because to be still in space is simply to be moving through time at the speed of light instead. There is no setting on the dial that reads 0. The total never drops below the speed of light, for you or for anything. The only way to stop moving through space-time altogether, to truly bring your total motion to nothing, would be to stop being an event in space-time at all, to stop existing. As long as you are here, as long as you are anything, you are moving at the speed of light through the fabric of the world, whether you spend that motion on space or on time. Motion is not something added on top of existence. It turns out to be the same thing as existence. To be is to move. That is a strange and bottomless thought to carry, and you may want to set it down for a while and return to firmer ground. So let us do exactly that. Let us come back from the abstract heights of space-time, back down to something solid and ordinary, something you can hold in your hand. Pour yourself an imaginary glass of cold water and set it on the table and let it sit there, perfectly calm, perfectly still. Here, surely, at human scale, in a glass of motionless water, is a small and honest piece of rest. The water is not going anywhere. Its surface is flat and quiet. Nothing about it is moving. And yet, if we shrink down and look closely, down past where the eye can follow, we will find that this calm glass of water is one of the most violent places we have looked at yet, a storm that never stops, hiding inside the stillest thing in the room. Part 7. The fire inside cold things. The calm of the water is a trick of scale, just as the calm of your own body was. Water is made of molecules, countless tiny particles far too small to see, and those molecules are never, ever at rest. In a glass of water at room temperature, the molecules are moving constantly, careening in every direction, slamming into one another billions of times each second, ricocheting off and colliding again in a frenzy that never pauses. The water looks still only because you are too large and too slow to see the storm. Average everything out across the whole glass, over all those uncountable little motions pointing every which way, and the bulk of the water sits quietly on the table. But the quiet is a statistical illusion laid over a chaos that does not stop. What we call temperature is nothing more than a measure of that motion. This is one of those facts that sounds almost too simple to be as important as it is. Heat is not a substance, not a fluid that flows into things to warm them. Heat is motion, the jostling and vibrating and racing of the particles that make a thing up. When you warm something, you are making its particles move faster. When you cool it, you are slowing them down. A hot cup of tea is hot precisely because its water molecules are moving more violently than the molecules in a cold cup. The warmth you feel when you wrap your hands around the cup is the molecules of the tea kicking the molecules of the cup, which kick the molecules of your skin, passing their motion along to you. Temperature is the speed of the invisible storm, translated into a number you can read on a thermometer, and the speeds in that storm are not gentle. In the air around you right now, the molecules of nitrogen and oxygen are moving at an average of something like 500 meters every second, faster than a rifle bullet, faster than the spinning ground beneath you. They do not travel far before colliding, because the air is crowded and a molecule can only fly a tiny distance before it slams into a neighbor. But in those tiny hops, they are moving ferociously fast. The same is true at slower speeds, in the water in your glass and in the solid surface of the table, where the atoms are locked in place but vibrate relentlessly around their fixed positions, trembling in a buzz that never stills. Everything you think of as solid and quiet is, on the inside, shaking. The stillness of ordinary objects is the stillness of a swarm, so fast and so small that it blurs into apparent calm. This restless motion is not confined to liquids and gases, where the particles can fly about freely. It fills solid matter too, every bit as much, only there the motion takes a different form. In a solid, the atoms are locked into place, bonded to their neighbors, unable to wander off. But locked in place does not mean still. Each atom quivers and vibrates around its fixed position, trembling back and forth millions upon millions of times every second, jostling against its neighbors in a buzz that never lets up. The table your hand rests on, the chair holding you up, the walls around you, all of them are humming with this trembling, every atom in them shaking in place. They feel solid and motionless to your touch only because the trembling is far too small and far too fast for your fingers to register. Touch the table, and you are touching a swarm held in formation, vibrating against your skin. You can sense the molecular storm more directly than you might think. When a smell crosses a room, when the scent of something cooking reaches you a moment later in the next room, you are sensing molecules that have physically traveled through the air to your nose, carried there by their own ceaseless motion, bouncing from collision to collision across the whole distance. When you hold a metal spoon in something hot and feel the warmth creep up the handle, you are feeling motion being passed along, atom to vibrating atom, from the hot end to your fingers. The motion is invisible, but its effects are not. They are in every smell you notice, and every warm thing you hold, quiet and constant evidence of a world that never stops moving, even when it looks perfectly still. For most of history, no one could prove any of this, because no one could see atoms or molecules at all. The storm was a hypothesis, and a controversial one, but there was a clue hiding in plain sight that turned out to be a direct window onto the invisible motion. In 1827, a botanist named Robert Brown was looking through his microscope at tiny grains suspended in water, and he noticed something he could not explain. The little grains were jittering. They danced and trembled and wandered erratically through the water, never holding still, shoved this way and that by nothing he could see. He checked that they were not alive, that there was no current, no draft, no trick of the apparatus. Still, they danced. He had no idea what was kicking them, and the puzzle of that ceaseless dance would carry his name for the better part of a century. We call it Brownian motion to this day. The answer came from the same mind that gave us relativity, and in the same astonishing year. In 1905, Einstein worked out that the dancing grains were being struck constantly and from every side by the water molecules around them, molecules far too small to see directly. A grain is large compared to a molecule, but it is small enough that the molecular bombardment does not perfectly cancel out. At any instant, slightly more molecules happen to strike one side than the other, and the grain lurches in response. A moment later, the imbalance points a different way, and the grain lurches again, tracing out the restless, random walk that Brown had seen. Einstein turned this into precise mathematics, predicting exactly how far the grains should wander, and a few years later, careful experiments by Jean Perrin confirmed every detail, work that earned him a Nobel Prize. The dancing grains were the fingerprints of the molecular storm. They were the first direct proof that atoms are real and that the unseen world is in perpetual, restless motion. Let yourself shrink down into that drop of water and watch it happen, because it is one of the strangest things you could ever witness. Imagine becoming small enough that a single grain, invisible to your ordinary eye, looms in front of you like a boulder hanging in the water. Around it, too small even now to see clearly, the water molecules swarm in their billions, each one a blur of speed. Watch them hammer the boulder from every direction at once, an endless, sleepless crossfire of impacts, thousands upon thousands every instant. See the boulder shudder and jump as the crossfire shifts, knocked left, then right, then up, never given even a fraction of a second to settle. There is no rhythm to it, and no rest in it. It is pure, ceaseless agitation, a thing being shoved forever by an invisible crowd that never tires and never stops. And this is happening right now in every glass of water, every puddle, every cell of your body, everywhere there is anything at all above the very bottom of the cold. So the stillness of the water was never real either. The glass of water, like your own body, like the spinning earth, is in furious motion that hides itself behind a calm surface. But this kind of motion seems, at first, to offer a way out that the cosmic motions did not. The molecular storm is just heat, after all, and heat can be removed. You can cool things down. Put the water in a freezer, and the molecules slow. Make it colder still, and they slow further. So a natural and hopeful question forms. If temperature is just the speed of the storm, then surely, if we could only make something cold enough, we could slow the storm all the way to nothing. We could bring the molecules to a perfect halt, and finally, at the very bottom of the cold, arrive at true stillness. There is even a name for the temperature where all that motion should cease, the coldest that cold can be. It is called absolute zero. And the story of what happens as we approach it is the story of running, again and again, into a floor we can never quite touch. Part 8. The floor you can never reach. Absolute zero is the temperature at which the motion would, in the simplest picture, finally stop. If heat is the speed of the particles, then there must be a coldest possible temperature, the point where the particles have given up all the motion they can give up and slowed as far as they can go. That point sits at about minus 273 degrees on the Celsius scale, a cold far beyond anything that exists naturally anywhere, even in the empty space between the stars, which is warmed ever so slightly by the leftover glow of the early universe. Scientists set their most fundamental temperature scale to begin right there, calling that coldest point zero. So that absolute zero is, by definition, the bottom. There is no colder. You cannot take away motion that is already gone. The dream, then, is simple. Reach absolute zero, and you reach perfect stillness. Take a clump of matter, cool it and keep cooling it. Draw out every last bit of its motion, and at the bottom of the cold, you will have made the one thing this whole night has been searching for. A truly motionless object, a piece of the universe at rest. It is a beautiful goal, and physicists have chased it for more than a century, building ever colder and more ingenious machines to creep down toward that floor. And what they have discovered, over and over, is that the floor will not let itself be touched. The closer you get to absolute zero, the harder every further step becomes, as though the cold itself were pushing back against you with rising strength the nearer you come. There is a law that says, this must be so, one of the basic laws of thermodynamics, and it carries a quiet finality. It states that you cannot reach absolute zero in any finite number of steps. Every method we have for cooling something works by removing a portion of the motion that remains, and as the motion left to remove grows smaller and smaller, each removal gets you a smaller and smaller distance, like trying to reach a wall by always stepping halfway there. You can get astonishingly close. You can halve the distance 1,000 times. But the number of steps needed to actually arrive is not large. It is endless. And endless is a thing no laboratory and no machine can ever complete. Absolute zero is not a destination that is merely difficult to reach. It is a destination that the structure of physics places permanently out of reach, an edge you may approach forever and never arrive at. It is worth understanding why each step toward the bottom costs so much more than the last, because it is not a failure of effort, but a feature of the cold itself. Every method we have for cooling something works by carrying its motion away into something colder, the way a warm drink gives up its heat to the ice around it. But as your sample creeps toward the very bottom, there is less and less of anything colder to carry the heat into, and the warmth you are trying to remove grows fainter and harder to grip. Taking away the last few scraps of motion is like trying to bail out the final drops of water from the bottom of a boat with a bucket made for gallons. The tools that worked higher up simply stop biting. Each further step down demands a new and more delicate trick than the one before, and the steps themselves keep getting smaller even as the effort keeps getting larger. The tricks that reach the very lowest temperatures are strange and wonderful in their own right. To slow atoms down, physicists shine finely tuned laser light at them from every side, so that an atom flying toward a beam is gently pushed back by the light itself, struck by particle after particle of it until its motion is bled away. Light, which we think of as weightless and gentle, is used as a brake, slowing the atoms toward a crawl. Magnetic fields then hold the chilled atoms in a trap, suspended away from any wall that might warm them, and the very fastest atoms are allowed to slip out, carrying the most motion away with them and leaving the slower, colder ones behind. With methods like these, working in falling towers and shielded chambers, physicists have crept to within trillionths of a degree of the bottom. And still, as they go, the cold pushes back and the floor stays forever just out of reach. And yet how close we have come is genuinely staggering and worth pausing on. In laboratories, physicists have cooled small clouds of atoms to within a hair of the absolute bottom, to temperatures measured not in degrees, but in billionths and even trillionths of a degree above zero. The coldest temperature ever produced, as far as I know, was made in a tall tower in Germany, a facility built for dropping experiments so they can briefly fall in something close to weightlessness. There, a team cooled a small cloud of around 100,000 atoms into a delicate quantum state, and then, as the whole apparatus fell freely down the tower, they used a careful arrangement of magnetic fields to slow the atoms further still, until the cloud reached a temperature of about 38 trillionths of a degree above absolute zero. For a couple of seconds, as it fell, that little cloud was very likely the coldest spot in the entire universe, colder than the farthest reaches of empty space, colder than anything nature makes on its own. Let yourself rest, for a moment, in how quiet that cold is. Picture the little cloud of atoms hanging in its chamber as the tower falls around it, sealed away from every disturbance, shielded from every stray bit of heat, drifting in the gentlest weightlessness. The motion that fills the rest of the universe, the racing molecules, the slamming and ricocheting, has here been hushed almost to nothing. The atoms barely stir. They drift so slowly that the ordinary words for speed hardly apply. It is the closest thing to silence that matter has ever achieved. A hush quieter than the cold between the galaxies, held for just 2 seconds at the bottom of a falling tower before the world rushed back in. If perfect rest existed anywhere, you might think, it would be here, in this hush, in this most patient and delicate cold that human beings have ever made. But 38 trillionths of a degree is not zero. It is unimaginably close to zero, closer than almost anyone would have believed possible a century ago. And still, it is not zero, and the gap that remains is not a small practical shortfall that better engineering will someday close. It is a gap the laws of physics will never permit us to cross, no matter how clever the machine or how patient the cooling. We will go colder, surely. We will reach trillionths and then perhaps quadrillionths of a degree. We will keep halving the distance to the floor for as long as we keep trying, and we will never, ever stand on it, because the floor recedes from us by law, staying always just below our furthest reach. The coldest place in the universe is still, by the strict measure, warm. And here is the twist that turns this from a story of engineering limits into something far stranger. The twist that takes us into the final and most absolute reason that stillness is forbidden. Suppose for a moment that we could cheat the law. Suppose some impossible machine could carry a clump of matter all the way down, past the trillionths and the quadrillionths, and set it gently at the exact bottom, at absolute zero itself. You would expect, at last, perfect stillness, every particle frozen in place, all motion finally and completely gone. That is what the simple picture promised. Cool a thing to the bottom, and its motion stops. But the simple picture is wrong, and it is wrong in a way that has nothing to do with how cold you can get. Even at absolute zero, even with every scrap of heat removed, the particles would still be moving. They would still refuse to hold still. Because down at the smallest scale, the world is governed by quantum rules, and those rules forbid perfect stillness outright, in a way that no amount of cooling could ever overcome. Part 9. The motion that cannot be removed. The rule that forbids it is called the uncertainty principle, discovered by Werner Heisenberg, and it is one of the strangest and most solid facts in all of science. At the smallest scales, the world does not work the way our intuition expects. A particle does not have a perfectly definite position and a perfectly definite motion at the same time. The two are linked, traded against each other, so that the more precisely one is fixed, the more thoroughly the other must blur. If you pin a particle down to a definite place, its motion becomes wildly uncertain. If you fix its motion exactly, its position smears out across space. You cannot have both sharp at once. The universe simply does not permit a particle to possess a definite location and a definite velocity together. This is not a limit on what we can measure. It is a limit on what a particle can be. Now ask what perfect stillness would require, and you see the trap close. A perfectly still particle would have to be sitting at a definite location, fixed in place, not wandering at all, and it would have to have exactly zero motion, a perfectly definite velocity of nothing. But that is precisely the one thing the uncertainty principle forbids: a particle with both its position and its motion pinned down completely at the same time. Perfect stillness demands a definite place and a definite zero speed together, and the most basic law of the small world says you may never have both. So a particle that is confined to a region, held in place, cannot also have zero motion. It is forced, by the very structure of reality, to keep some irreducible jitter, some residual trembling that can never be removed. Physicists call it zero-point motion, the motion that remains at the 0 point of temperature, the motion you cannot cool away because it was never made of heat in the first place. This is the thing I most want you to carry away from tonight, so let me say it as plainly as I can. The stillness you have been chasing all evening is not merely hard to reach. It is not a practical goal that we keep falling just short of because our machines are not yet good enough. It is forbidden. A perfectly motionless particle is not a difficult thing to make. It is a thing the laws of physics do not allow to exist at all. In the same way, they do not allow a particle to be in two places with no connection between them or to have a temperature below the bottom of cold. Your stillness was never an option that the universe placed just out of reach, waiting for you to work harder and seize it. It was never on the table. The most basic law of the small world struck it off the list of possible things before you, or the earth, or the first star, ever existed. You cannot be still, not because you have failed, but because being still is not among the things that matter is permitted to do. And this is not some abstract claim that lives only in equations and can never be checked. The 0 point motion is real enough to produce effects you could, in principle, hold in your hands. The clearest example is a strange and beautiful substance called helium. Helium is the second lightest element, its atoms exquisitely small and light, and the forces between helium atoms are unusually weak. When you cool almost any other substance far enough, its particles slow down enough for their mutual attraction to lock them into a rigid crystal, a solid, and the thing freezes. But helium never freezes, not at ordinary pressure, not even if you cool it all the way down to the very bottom of the cold, to a hair above absolute zero. It stays a liquid forever. It is the only substance in the universe known to do this, and the reason is exactly the motion we have been describing. The helium atoms are so light, and their grip on one another so feeble, that their unavoidable 0 point motion, the jitter the uncertainty principle forces upon them, is strong enough to keep them from ever settling into a crystal. Cool the helium as far as you like, take away every last bit of heat, and still the atoms tremble with their irreducible quantum motion, jiggling too much to lock into place, refusing to freeze. The liquid stays liquid down to the coldest temperature there is, kept fluid not by warmth, but by the motion that warmth has nothing to do with, the motion that remains when all the warmth is gone. A cup of liquid helium at the bottom of the cold is a thing you could, in a sense, look at, a visible, pourable proof that motion survives even the total absence of heat, that the trembling at the bottom of the world cannot be stilled. So we have now found a second, completely separate reason that stillness cannot exist, and it is worth noticing how different it is from the first. Out among the galaxies, stillness failed because there was no fixed background to be still against, no absolute rest anywhere in the universe to hold yourself to. That was a fact about space and motion at the largest scale. Here, down among the atoms, stillness fails for an entirely different reason, because the laws of the small world forbid any particle from holding a definite place with 0 motion. These two prohibitions have nothing to do with each other. One comes from relativity, one from quantum mechanics, two pillars of physics that famously do not even agree with each other about much. And yet both, independently, in their own language, deliver the same verdict. There is no such thing as rest. The universe has locked the same door twice, with two different keys from two different directions. It would be enough, you might think, to forbid stillness for matter, for atoms and particles and the things they make. But the universe goes further than that, further than seems necessary, in a way that is almost excessive. You might imagine that if you took a region of space and removed every particle from it, every atom, every speck of matter, every bit of light, you would at last have a place of perfect stillness. Empty space, with nothing in it to move, must surely be the one truly motionless thing. Pure nothing cannot tremble. And yet it does. The emptiness itself, the vacuum with everything taken out of it, turns out to be restless, flickering, never still. Even nothing, it seems, is not allowed to hold its breath. To see how that can possibly be, we have to look at what empty space is actually made of, which is not nothing at all. Part 10. The Trembling of Empty Space. We tend to think of empty space as a kind of pure absence, a container with nothing in it, an inert backdrop where things happen. Take away the air, the dust, the light, every last particle, and what remains is supposed to be true nothingness, perfectly quiet, because there is nothing there to make a sound or a stir. But this picture, comforting as it is, turns out to be wrong. Modern physics describes the things we call particles not as tiny solid grains, but as ripples in invisible fields that fill all of space. An electron is a ripple in an electron field. A particle of light is a ripple in the electromagnetic field. These fields are everywhere, underlying everything, present even where no particles are, and a field, by its nature, can never be perfectly flat and perfectly still, for exactly the same reason a particle cannot. The uncertainty principle, the same law that forbids an atom from sitting still, also forbids these fields from lying perfectly quiet. A completely flat, completely motionless field would have, at every point, a definite value and a definite rate of change, both pinned to zero at once, and that is the very thing the uncertainty principle does not allow. So the fields cannot rest, even in the emptiest region you could imagine. With every particle removed, the fields that fill space must still quiver, trembling with a faint, irreducible motion that physicists call vacuum fluctuations. The emptiness is not empty. It is a sea of restless fields, humming with the lowest motion they are permitted to have, a motion they can never give up, because giving it up would break the most basic rule of the small world. The vacuum has a 0-point motion of its own. Out of that restless humming, the vacuum does something that sounds like fantasy but is solidly part of physics. The fluctuating fields are constantly producing tiny, fleeting disturbances, pairs of particles that flicker into being and almost instantly vanish again, borrowing a scrap of energy from the uncertainty of the vacuum and paying it back before the universe can notice. These are sometimes called virtual particles, and they appear and disappear everywhere, all the time, throughout all of space, a perpetual, microscopic foam of creation and annihilation. Empty space, looked at closely enough, is not a calm void, but a seething, boiling churn, never still, for even the briefest instant, frothing with motion that comes from nothing and returns to nothing without pause. Let yourself go and stand inside it, in your imagination, because there is no stranger place in all of physics. Picture a small box, sealed and shielded, with every atom pumped out of it, every particle of light excluded, cooled as near to the bottom of the cold as the universe allows. By every ordinary measure, the box is empty. There is nothing in it. And now shrink down and look closely at the nothing. It is not still. The fields that fill the box are shivering everywhere at once, a fine and ceaseless trembling with no source you can point to. Watch pairs of ghostly particles wink into existence and vanish again before you can fix your attention on them. Here, then there, then everywhere, a silent snowfall of things that barely manage to be. There is no quiet in this emptiness, no rest, no moment of true stillness anywhere in it. The nothing itself is in motion, and it has been since the universe began, and it will be forever. And, lest you think this is only a story physicists tell, a way of talking that need not be taken literally, the trembling of the vacuum produces a force you can actually measure. Back in 1948, a physicist named Hendrik Casimir worked out a remarkable prediction. If you placed two flat metal plates extremely close together in empty space, he reasoned, the restless fluctuations of the vacuum between the plates would be slightly restricted because only certain ripples fit in the narrow gap, while the fluctuations outside the plates are not restricted at all. That imbalance, more trembling outside than inside, would push the two plates together, as though the seething vacuum were pressing on them from without. A force, arising from the motion of empty space itself, pushing on solid objects with nothing visible between them. For decades, this was a prediction on paper, exquisitely difficult to test because the force is so tiny and the plates must be brought so impossibly close. But in 1997, careful experiments finally measured it directly, and the force was there, exactly as the trembling vacuum demanded, matching the prediction to within a small margin. The plates were drawn together by the restlessness of nothing. Think about what that means. The motion of empty space is not a figure of speech or a mathematical convenience. It is real enough to move solid metal, real enough to detect with an instrument, a measurable push delivered by a vacuum that refuses to be still. We have weighed the trembling of the void and found it has a force. Even nothing, the purest and emptiest nothing the universe can offer, is in motion, and that motion leaves fingerprints on the world. So now the picture is nearly complete, and it is more total than we could have guessed when we began, with the simple feeling of sitting still in a quiet room. Stillness fails for the galaxies, because there is no fixed background to be still against. Stillness fails for matter, because the uncertainty principle forbids a particle to hold a definite place with zero motion. And stillness fails even for empty space, because the fields that fill the vacuum can never lie flat and tremble with a motion you can measure as a force. Every level we have looked at, from the largest to the smallest to the emptiest, delivers the same verdict by its own separate law. There is motion in the stars, motion in the atoms, motion in the nothing between them, and nowhere, at any scale, is there rest. The universe has run out of places where stillness might have hidden. Which leaves us with a question we have been circling all night without quite asking outright, and it is perhaps the strangest question of all. We have seen that the universe will not permit anything to be still, that it has built law upon law to forbid rest at every level. But why is there any motion in the first place? Forbidding stillness is one thing, but the prohibition would be empty if there were nothing moving to begin with. Something had to set the galaxies falling, set the atoms trembling, wind up the great spinning wheels of the stars and the planets. The motion did not come from nowhere. It was started, somewhere, somehow, and then never stopped. To understand why everything is moving, we have to ask where all of this motion came from, and why, once it began, it has never run down. The answer reaches back to the very beginning of the universe, and to a simple law about why moving things keep moving. Part 11. Why it all began to move. For most of human history, people believed the opposite of the truth about motion, and the mistake is an understandable one. Watch the world around you, and it certainly looks as though rest is natural and motion must be maintained. Push a cart and it rolls for a while, then slows and stops. Throw a stone and it flies, then falls and lies still. Everything that moves seems to wind down and come to rest unless you keep pushing it. The ancient philosopher Aristotle drew the obvious conclusion, and his view held sway for 2,000 years. He taught that rest is the natural state of things, the condition everything returns to when left alone, and that motion is the exception, something that requires a continuous cause to keep it going. Stop pushing, and the natural stillness reasserts itself. It is exactly what your eyes seem to tell you, but your eyes are being fooled by an invisible thief, and the thief is friction. The cart slows because the ground and the air are constantly stealing its motion, rubbing it away into heat. The stone falls because gravity pulls it down. In every everyday case, there are hidden forces draining the motion out of moving things, and those forces are so universal on the surface of the earth that they hide the real law underneath. It took the genius of Galileo, and then of Isaac Newton, to see past the friction to the truth, and the truth is the reverse of what Aristotle believed. A moving object does not naturally slow down. Left truly alone, with no force acting on it, a moving object keeps moving forever, in a straight line, at a constant speed, never stopping of its own accord. Motion does not need a cause to continue. It only needs a cause to change. This principle is called inertia, and it is the first of Newton's laws of motion. This single idea overturns the ancient picture completely, and it is worth feeling the full weight of the reversal. It is not motion that requires explanation. It is stopping. A thing in motion will stay in motion, untroubled, indefinitely, unless something actively intervenes to slow it. The planets are the perfect demonstration. Out in the near emptiness of space, there is almost no friction to steal their motion, and so they have been circling the sun for more than 4.5 billion years, without any engine, without any push, coasting on the motion they have always had. The Earth does not orbit because something keeps shoving it along. It orbits because nothing stops it. Once moving, it simply continues, as inertia says it must. The motion we have been cataloguing all night, the spinning and the orbiting and the falling, needs nothing to sustain it. It persists on its own. The real question was never why it keeps going. The real question is how it got started. And the answer is that the motion is old, far older than the Earth or the Sun, inherited from the conditions of the early universe and passed down, conserved, from one generation of structure to the next. Physics has a set of bedrock principles called conservation laws, and one of the most important says that the total motion in a closed system, properly accounted for, cannot simply be created or destroyed. Motion can be passed from one object to another, shared and redistributed, but the books must always balance. The grand total carries forward. So the motion in the universe today was not made today. It was handed down, traced back through an unbroken chain of cause and inheritance to the very beginning, when the universe burst into existence, already expanding, already in motion, in the event we call the Big Bang. You can feel this conservation at work in something as simple as firing a gun. When the bullet leaps forward, the gun kicks back hard against your shoulder, and that kick is not an accident or a flaw. It is the universe keeping its books balanced. The forward motion, handed to the bullet, has to be paid for exactly, and it is paid for by the backward motion of the gun, so that the total motion of gun and bullet together, added up with direction taken into account, is the same after the shot as it was before, which is to say, no net motion in either direction. Nothing in the universe can simply start moving on its own without something else moving the opposite way to balance it, and nothing can stop without handing its motion to something else. Motion is never made out of nothing and never destroyed into nothing. It is only ever passed around, traded from one thing to another, with the grand total held fixed for all time. That is why the motion of the early universe could not simply fade away. It had nowhere to go. It could only be inherited, again and again, down the long chain of collapsing clouds and forming stars, until it reached the spinning world you rest on tonight. There is a particular kind of motion whose inheritance is especially beautiful to follow, and that is spinning, because nearly everything in the universe spins. The Earth spins, the Sun spins, the whole galaxy turns, and almost every object large enough to see rotates in some fashion. This near-universal spinning comes from another conservation law, the conservation of rotational motion, and the way it amplifies is something you have seen with your own eyes. Picture a figure skater turning slowly on the ice with her arms stretched wide. When she pulls her arms in close to her body, she suddenly spins faster, dramatically faster, without pushing against anything. She did not add any spin. She simply gathered the spin she already had into a smaller space. And the law that conserves rotational motion demands that as the spinning matter draws inward, it must turn more quickly to keep the total the same. Smaller means faster. It is automatic, and it is unavoidable. Now, take that same principle and apply it to the birth of a star, because that is precisely where the spinning of the world comes from. Stars and their planets form from immense clouds of gas and dust drifting in space, clouds light years across. Such a cloud is never perfectly motionless. It always has some faint, almost imperceptible drift and turn to it, the gentlest possible rotation. And then gravity begins to pull the cloud inward, collapsing it down from something light years wide into something the size of a star and its planets. As the enormous cloud shrinks, exactly like the skater pulling in her arms, its slow initial turn is gathered inward and amplified, faster and faster, until what began as the barely there drift of a great cloud becomes the brisk spin of a finished star and the swift orbits of the planets wheeling around it. This same inward gathering of spin explains something you might never have thought to ask about, which is why the solar system is flat. The planets do not orbit the sun every which way, some going over the poles and some around the middle, like bees swarming a hive. They all circle in nearly the same plane and all in the same direction, as though laid out on an invisible tabletop. That flatness is a direct result of the spinning collapse. As the great cloud fell inward and turned faster, it also flattened, spreading out into a turning disk, the way a spinning lump of dough flattens into a wide circle when a baker tosses and spins it in the air. The matter that became the planets formed within that disk, already sharing its single direction of turn, and so the planets inherited not only their motion, but the very plane they move in. The orderly, flat, same-way turning of the solar system is a fossil of the cloud it was born from, a memory of motion preserved for more than 4.5 billion years, and it will be preserved for billions more. The Earth's spin, its year-long orbit, the sun's own rotation, all of it was inherited from the turn of the cloud that made them, concentrated and sped up by the simple law that smaller must mean faster. So when you trace the motion back, you find it has no beginning that is its own. The Earth's orbit was inherited from the collapsing cloud. The cloud's slow turn was inherited from the swirling motion of the galaxy. The galaxy's motion was inherited from the uneven, expanding flow of matter in the young universe. And all of it, every spin and every drift and every orbit, goes back to the single fact that the universe did not begin in a state of stillness and then start moving. It began already in motion, already expanding, already flowing, and the laws of inertia and conservation have simply carried that original motion forward, reshaping it endlessly, but never letting it die. We are not living in a universe that was once still and then was disturbed. We are living in the ongoing momentum of the beginning itself, a motion that was never started because it was there from the first instant, and that has never stopped because nothing made to stop it. This is the answer to where the motion comes from. But it raises one more question, the one that takes us to the largest scale of all, and to the strangest stubbornness in the whole story. We have spoken of the galaxies moving through space. But it turns out that even space, the supposedly fixed stage on which everything moves, is not holding still. The container itself is in motion, swelling and stretching, carrying the galaxies apart from one another. And the discovery that space refuses to be still was so unwelcome, even to the greatest physicist of the age, that he changed his own equations to deny it, in what he would later call the biggest mistake of his life. Part 12. The universe that would not hold still. When Einstein finished his theory of gravity in 1915, a fuller and more complete vision than anything before it, he turned it toward the universe as a whole and ran into something he did not like. His equations, applied to all of space and all of its matter, would not sit still. They insisted that the universe must be doing something, either expanding or contracting, swelling outward or collapsing inward, but never simply staying the same. A universe full of matter cannot hold a fixed size, because gravity pulls everything together, and a static universe would begin to fall inward under its own weight. The mathematics was telling Einstein that the cosmos is dynamic, that space itself is in motion. And Einstein, like nearly everyone of his time, was certain that the universe was static, eternal, and unchanging, a fixed and stable stage that had always looked more or less as it does now. So he did something he would come to regret. To force his equations to describe the still, unchanging universe he believed in, Einstein added a new term by hand, a kind of counterforce woven into space itself, pushing outward just hard enough to balance the inward pull of gravity and hold everything motionless. He called it the cosmological constant, and its only purpose was to keep the universe still. With it, his equations could at last describe a cosmos that neither expanded nor collapsed, a universe frozen at a fixed size, exactly the kind of eternal, restful stage he expected reality to be. He had reached into the most fundamental description of space and time, and inserted a term whose whole job was to forbid the universe from moving. It was, in a sense, the grandest attempt at stillness ever made, an effort to nail down not an atom or a cloud of gas, but the entire universe. The universe, of course, refused. In the years that followed, the astronomer Edwin Hubble, working with one of the great telescopes of the day, made a discovery that would dismantle the static picture entirely. He found that the distant galaxies are not sitting at fixed distances from us. They are moving away, almost all of them, and the farther away a galaxy is, the faster it is receding. This is exactly the pattern you would see if the whole universe were expanding, every region of space stretching apart from every other, carrying the galaxies away from one another like markings on the surface of an inflating balloon. By 1929, the evidence was clear and public. The universe is not static. It is growing. Space itself is swelling, and the galaxies ride that swelling apart. The fixed and eternal stage that Einstein had bent his equations to preserve had never existed at all. It is important to be clear about what this expansion actually is, because it is easy to picture it wrongly. The galaxies are not flying apart through space like fragments hurled outward from a bomb, racing away into some pre-existing emptiness. It is space itself that is stretching, swelling between the galaxies and carrying them apart on the growing distance. The usual picture is a balloon with dots inked on its surface. As you blow the balloon up, every dot moves away from every other dot, not because the dots are crawling across the rubber, but because the rubber between them is stretching. Each dot stays exactly where it was painted, and still they all separate, because the surface they sit on is growing. The galaxies are the dots, and space is the rubber, and there is no center to the expansion and no edge, only everything drawing away from everything else as the space between it all swells. The way Hubble saw this was through the light of the galaxies themselves. When a galaxy is carried away from us by the stretching of space, the light it sends out is stretched along with the space it crosses, Its waves pulled longer and shifted toward the red end of the spectrum. The faster a galaxy recedes, the more its light is stretched, and the farther away it is, the faster it goes. So the most distant galaxies show the greatest stretching of all. Hubble measured this reddening across galaxy after galaxy and found the pattern unmistakable. The light of the universe was telling him that space was growing, that the distances were opening up everywhere, that there was no still and settled cosmos at all. And every observer, in every galaxy, would see the very same thing, everyone watching everyone else drift away, because there is no special place in an expanding universe, no center holding still while the rest moves. Everything moves away from everything, everywhere, at once. Einstein abandoned the cosmological constant as soon as the expansion was established, setting it to nothing and calling it unnecessary. The physicist George Gamow later reported that Einstein had told him the introduction of that term was the biggest blunder of his life, and whether or not he used those exact words, the regret behind them is easy to understand. His own original equations had been trying to tell him the truth. They had insisted that the universe must move, that space could not hold still, and he had not believed them. He had trusted his intuition that the cosmos must be at rest over the mathematics that was quietly telling him it could not be. Had he trusted the equations instead, he might have predicted the expansion of the universe years before anyone observed it, one of the greatest predictions in the history of science. Instead, he reached for stillness, and stillness was the one thing the universe would not give him. There is a final irony in this story, and it sharpens the lesson rather than softening it. Decades later, in the closing years of the 20th century, astronomers discovered that the expansion of the universe is not merely continuing but speeding up, the galaxies flying apart faster and faster as time goes on, driven by some mysterious property of space that physicists now call dark energy. And to describe it, they reached back for the very term Einstein had thrown away, the cosmological constant, now repurposed not to hold the universe still, but to account for its accelerating motion. The thing he invented to enforce stillness turned out to describe the opposite, an extra push that makes the cosmos expand ever more quickly. Even the term meant to freeze the universe in place came back as a description of motion. Space will not be held. It stretches, and it stretches faster every day, and there is no version of the equations and no era of cosmic history in which it simply rests. So, we have now followed the refusal of stillness all the way up to its largest possible expression. It is not only that the things in the universe move, the planets and stars and galaxies, it is that the container holding them, space itself, the very stage we imagined as the fixed and motionless background, is also in motion, swelling outward in every direction, carrying everything apart. There is no still stage, and there are no still actors. The motion goes all the way up to the universe entire, and all the way down to the trembling of empty space, and it is the same refusal at both ends. Nothing rests. Not the atom, not the star, not the galaxy, not the void between them, not the fabric of space itself. The universe is motion, top to bottom, beginning to end. Which brings us, at last, to the final question, the one that has been waiting at the end of the night since we began. If everything is in motion, and has been since the first instant, and the laws of inertia and conservation carry that motion forward without letting it die, then is there any end to it? Will the motion ever run down? Could the universe, given enough time, finally exhaust itself and coast to a stop, arriving after countless ages at the perfect stillness it has denied us at every turn? There is a far future the universe is heading toward, and people have wondered for a long time whether it is a kind of death, a great stillness at the end of all things. And the truth about that ending is the gentlest and strangest part of the whole story. Part 13. Will the motion ever stop? There is a direction to time, a one-way flow that we all feel, and it comes from the way motion spreads out and shares itself around. A hot cup of coffee in a cool room always cools down. It never spontaneously grows hotter by drawing warmth from the air. A drop of ink in water always spreads until it is evenly mixed. It never gathers itself back into a single drop. This tendency for energy and motion to spread from where they are concentrated to where they are not, until everything reaches the same level, is one of the most reliable patterns in all of nature, and it defines the forward direction of time. The future is the direction in which things even out. Physicists measure this spreading with a quantity called entropy, and the rule is that the entropy of the universe as a whole always increases. Motion never vanishes, but it disperses, flowing from the hot to the cold, from the ordered to the mixed, smoothing itself out across everything. Follow that tendency far enough into the future, and you arrive at a fate that has unsettled people since it was first imagined, sometimes called the heat death of the universe. Picture the cosmos ages from now, almost unimaginably far ahead. The stars have all burned through their fuel and gone dark, one by one, until the last of them flickers out. The galaxies have drifted apart, carried away by the endless expansion of space, until each is alone in the dark. All the concentrated energy that once drove suns and lit worlds has spread itself out as evenly as it possibly can, until there are no more differences left to drive anything, no hot places and no cold places, only a uniform, lukewarm sameness stretched across an emptiness that grows colder and emptier forever. Nothing burns, nothing forms, nothing happens, because making things happen requires a difference, and all the differences have been spent. It sounds, on its face, like the ultimate arrival of stillness, the final rest the universe denied us, reached at last when the cosmos finally runs down. But it is not stillness, and the reason is the thread we have followed all night. Heat death is not the absence of motion. It is the most even possible sharing of motion, which is a very different thing. In that far future, the particles are still moving, still drifting, still trembling with the quantum jitter that no cold can remove, still riding the swelling of a space that goes on expanding. What has ended is not motion, but unevenness, the differences that let motion be gathered and used. The universe, at its heat death, is not a frozen statue. It is a thin, cold, endless stir. Motion spreads so evenly that nothing can be built from it, but motion all the same, and motion that never stops. Even at the supposed end of all things, with the stars gone and the differences gone, the universe is still in motion, because the laws that forbid stillness do not switch off when the lights go out. They hold to the very end, and past it forever. It is worth letting the timescales of this future settle on you, because they are part of why it feels less like an ending than a slow fading. The last ordinary stars will burn out in something like tens of trillions of years, a stretch of time so long that the entire age of the universe so far, all 13.5 billion years of it, is less than 1,000th of it. After that come the long ages of the stellar remnants, the cooling embers and collapsed cores, drifting for spans of time with so many zeros that ordinary names for numbers give out. And still the universe goes on, thinning and cooling, the motion never stopping, only spreading and gentling, across durations next to which the whole bright history of stars and planets is a single flicker at the very beginning. Stillness does not arrive, even given all of that time. The motion simply grows quieter and more patient, and keeps going, with all the time in the world, and nothing left to spend it on. This is the place to be honest about a hope that people return to again and again, because the eternal motion of the universe is so often misunderstood. If everything is always moving, the thought goes, and the motion never stops, then surely we could tap into it, harness the endless trembling of the atoms or the restless energy of the vacuum, and draw out a limitless supply of free power, a machine that runs forever on the motion that never dies. It is an old dream, the dream of perpetual motion, and it has never once worked, not because inventors were not clever, but because the same law of spreading that gives us the arrow of time forbids it. You can only get useful work out of motion when there is a difference to exploit, something hot beside something cold, something fast beside something slow. The ceaseless motion of the universe is real, but as it spreads towards sameness, it becomes less and less able to do anything, and you can never extract a free and endless supply from it. The atoms tremble forever, and the vacuum hums forever, but neither will ever turn a wheel for nothing. The motion is eternal, the free lunch is not. Both of these are true at once, and only the first of them is strange. So let us go there, to the very end, and see it for ourselves, because it is not the frightening place its name suggests. Imagine drifting in the universe an almost endless stretch of time from now, long after the last star has died. The dark around you is complete, and the cold is lower than any cold that exists today, and the galaxies are gone, carried over the horizon by the expansion, until not one of them remains in view. Nothing here burns, nothing here shines. It is the quietest the universe will ever be, the closest it will ever come to the rest we have been chasing all night. And yet reach down into that final dark and feel it carefully, and you will find it is not still. The faint particles drift, the fields tremble with the same zero-point motion they have always had. Space itself stretches on, slow and patient and endless. The universe, even here, even now, at the farthest edge of time, has not stopped moving. It simply moves more gently than it ever has, a sleeping stir that goes on and on, with nothing left to disturb it and nothing able to bring it to an end. And so we come back, at the last, to the question we began with, the simple one, the one that seemed almost too easy to ask. What is wrong with stillness? After everything, the answer turns out to be nothing at all. There is nothing wrong with stillness. It is a perfectly lovely idea, calm and restful, and genuinely appealing to a tired mind. The trouble is not that stillness is bad. The trouble is that it does not exist, and never has, anywhere, at any scale, in the entire history of the universe. It is forbidden out among the galaxies, where there is no fixed place to be still against. It is forbidden down among the atoms, where the most basic law of the small world will not allow it. It is forbidden in the cold, where the floor of absolute zero can never be reached. It is forbidden in the empty vacuum, which trembles with a force we can measure. The universe did not begin still and then start to move. As far back as we can see, and as far ahead as we can imagine, it has only ever moved. Stillness is not a state the universe fell out of. It is a place the universe was never able to be. You went looking, at the start of tonight, for somewhere to stand still, a fixed and quiet floor beneath all the motion. And what you have found is that the floor was never there, that there is nowhere in all of existence to plant your feet and say, "Here, at last, is rest." That could be a lonely thought, but I would ask you to turn it over and hold it the other way, because there is something steadying in it once you do. You are not a still thing that the universe disturbed. You never were. You are a pattern made of motion, a small, persistent stirring in a universe that has been moving since its first instant and will be moving past its last. The motion is not something happening to you. The motion is what you are, and it is the one thing about you that connects you, unbroken, to the spinning earth and the falling galaxies and the trembling of empty space and the very beginning of everything. The stillness you imagined beneath your life was never the truth of you. The motion was. And the motion, alone of all things, never ends. So as you lie there now, feeling as still and settled as you have ever felt, let the feeling stay, but let the meaning of it change. You are turning with the earth and falling around the sun and streaming around the galaxy and drifting through the cosmos at 600 kilometers a second and trembling in every atom, and racing forward through time at the speed of light, all at once, in perfect comfort, and none of it disturbs your rest in the slightest. That is not a contradiction. That is what you are. You have never been still, not for one instant since before you were born, and you never will be, and the quiet you feel tonight is not the absence of motion. It is motion so smooth, so shared, so faithful, that it has carried you your whole life without once asking you to notice. Rest in it. It will not stop. It has never stopped. And somewhere far below the feeling of stillness, in the steady turning of a universe that cannot hold still, you are already, always, gently on your way.